When performing the scoring analysis, we determined that ground mission time and average lap time were the most influential score factors, followed by sensor weight and sensor length. Therefore, we optimized our plane to be fast and easy to load.
We decided to use the maximum 5-foot wingspan to generate as much lift as possible. In addition, we used the high wing configuration to increase flight stability for the towing mission while improving ease of manufacturing. A carpet plot and constraint diagram were used to optimize wing area and calculate the thrust-to-weight ratio for motor sizing based on the maximum lift coefficient that an SD7062 airfoil can produce at the predicted Reynolds number.
MATLAB was used to optimize the horizontal and vertical tail volume coefficients based on the horizontal coefficient range of 0.5 to 0.7 and a vertical coefficient range of 0.04 to 0.07. Lever arm distance was calculated for every possible vertical and horizontal volume coefficient combination until only 5 of reasonable length were optimized and navy out. The final horizontal and vertical tail volume coefficients were 0.52 and 0.04 respectively. The static and dynamic stability derivatives were in a variable range according to military specification stability document.
For control architecture, the transmitter communicates with the receiver and the receiver then communicates to the other components in the plane. The channel 1 port is designated for controlling the motor through the electronic speed control. Channels 2 through 4 are used to communicate with the control surface servos. Channel 5 is used to trigger the LED pattern in the sensor module, and Channel 6 is used to activate the deployment winch motor. The battery selection process prioritized reducing weight while still sustaining the desired flight time. Therefore, 2 6-cell 3200 mAh LiPo batteries in parallel were chosen. eCalc was used to assist with motor selection in addition to checking the flight time against parameters such as charge capacity and throttle percentage.
The total length of the fuselage is 53 inches with the constant geometry portion manufactured with 0.1 inch thick balsa core carbon fiber composite ribs for the constant geometry section, 3/4 inch thick basswood ribs for the end connection, and carbon fiber rods to hold everything together. The carbon fiber composite was made and CNC'd here at UAB. The nose and the tail cone were 3D printed with PETG. The total weight of the fuselage is 4 pounds. The wing and the stabilizer were manufactured from balsa, basswood, and carbon fiber tubes. The SD7062 wing had a 5-foot wingspan, 1.3 foot chord, and weighs 2.4 pounds. The horizontal stabilizer had a NACA 12 airfoil, a 24.7 inch span, and an 8.2 inch chord. The vertical stabilizer had a taper of 0.4, a 9.5 inch span, and a 6.3 inch average chord length. The total tail assembly weighs 2.3 pounds.
We predicted the performance of the aircraft by developing a model in MATLAB to simulate each of the flight missions. Each segment of flight was estimated using Euler's method to calculate velocity, position, and energy consumption. Thrust was calculated using propeller and motor performance data from the distributors. Lift and drag was collected using coefficients derived from aerodynamic analysis. The model predicted an average lap time of 40.3 seconds in Mission 2 and 13 total laps in Mission 3.
We determined that a conventional, high-wing, single-propeller aircraft would meet the needs of the competition. When fully loaded, the aircraft would weigh no more than 15 pounds. In order to reduce weight, the entire aircraft was skeletonized. This involved using a ribbed construction for the wing, horizontal and vertical tail, and fuselage, and shelling the nose cone and tail cone, and implementing a truss structure in order to remove as much unnecessary material as possible. The entire plane was modeled and assembled in SolidWorks, allowing for the creation of complex structures and shapes, easy modifications to better the design and adjust it for manufacturing, and easy generation of drawings, such as this 3-view drawing here.
The results of a year of labor. As you can see, our aircraft matches the design outlined in our 3-view drawing. Our aircraft currently shows the payload configuration, which uses a 3-blade propeller, as it generated the most thrust, while our 3-view drawing shows the 2-blade propeller that we plan to use for missions 1 and 3. For the ground mission, we showed a functioning deployment and retrieval mechanism with an operational sensor light pattern.
The deployment servo's 3 outputs, which are to turn clockwise, counterclockwise, or stay at rest, are determined by the inputs, which are the 3 possible positions of the stick switch on the transmitter. The Channel 6 port on the receiver sends these inputs to the winch controller, which then outputs it to the winch deployment servo. The sensor circuit was designed with a microcontroller to read in the values determined by the PWM signal from the receiver to activate the LED patterns. There are 2 discrete inputs available from the Channel 5 port of the receiver, with a higher value input as the trigger for the code to run the patterns.